Hi everyone, thank you so much for joining us today. Welcome to our June webinar. This month we're talking about mitigating construction risk with wireless condition monitoring. I'm Amna Youssef, I'm the Events and Marketing Executive here at Senceive. So just before we begin the webinar, I'll just run through a few housekeeping notes. We will be having a short Q&A session at the end of the webinar, so please do feel free to pop some questions into the question box. And also the webinar will be recorded and sent out to everyone who's registered. Okay, so I'd like to introduce you to our speaker today, Simon Brightwell. Simon comes with nearly 4 decades of experience in the delivery and marketing of testing, site investigation, survey and monitoring. He has a broad range of experience in the construction and infrastructure sectors. So over to you, Simon.
Thank you, Amna, for the introduction. Yeah, so it's a relatively short time slot for a pretty big topic here. So I think I'm going to skim the surface, but hopefully provide a little bit of something for everybody. Construction risk and how wireless monitoring can help you manage and mitigate it. Well, I think I'm going to start by considering first a little bit about construction. Typically, a construction project is going to involve a number of stages. Maybe it will typically involve some demolition of what's already there. It can involve excavation and foundation work in the ground. It can involve temporary works, and it can involve interaction with third-party properties, as well as construction of the new building or the structure that you're actually taking as your primary task. So I think monitoring needs to be considered as something which can deliver something useful at all of those stages, really, all 5 of those stages. At each of those stages, I think there are risks. They vary. I think there are risks of damage to third parties and a need to defend yourself against claims and litigation, as well as to prevent them happening in the first place, of course. There's a risk of injury or there are risks of inherent defects being built into a structure, which could arise later as being the basis of expensive claims. I think monitoring can play a role in detecting those early and preventing them. And there is a risk of delay, which can affect not just program, but also budget. So I think monitoring needs to address, I think, all of those if it's really to earn its keep. And I think that the need for data, we need data in various forms. It needs to be timely, it needs to be accurate, reliable, it needs to be accepted by different parties within the construction team. And there's a number of ways that we can get that. We can do visual survey. We can get out there and do visual survey, do conventional, traditional survey. We can take samples or do non-destructive testing. We could do attended monitoring, repeated survey to gather data and compare against the baseline to compare it over time. Or we can install a remote monitoring system to collate and collect data and to transmit it to a remote user. And as you may have gathered, since I'm sitting here giving a presentation about it, I'm quite a big fan of that option, really, the remote condition monitoring option. So let's address that a little bit further. Why are we interested in wireless monitoring? Why are we interested in the advantages of remote monitoring? Well, I think there are plenty of these. It's an IoT technology. Like other IoT kit, it's quick and easy, and you don't need a particularly high level of specialist skill to install it, to use it, to make sense of it. It's flexible. The sensors can be fitted in a whole variety of different ways. They're small. People don't often notice they're there. So if you need discrete equipment that doesn't upset people, particularly third parties, it can be quite suitable. It's strong and robust. It doesn't have a lot of wires that get damaged in a busy construction environment. It generally doesn't require line of sight. It is automated in most situations, therefore the number of site visits, the man hours that are required on site are much less than a conventional survey approach. It can provide a long life, and it can be moved around the site as your construction develops, so it can deliver a level of flexibility, I think, that stacks up well. So let's have a look at a construction environment. The places I think that this sort of technology can deliver include in the ground, geotechnical data. They include temporary works like the crane base that we can see here. They include the structure that's being built. They include the retained facade that you can see in the back here, so vulnerable parts of the structure, excavations and foundations, as well as historic properties or neighboring properties that may be affected by surface or subsurface construction. So looking a little bit more in depth here, we can see that we've got below the ground, we've got data being harvested from sensors in boreholes. These can include piezometers or inclinometers and extensometers. We've got tilt nodes in various places around this site. We've got equipment to monitor temperature, tilt beams where a number of tilt sensors are installed onto a beam, an optical displacement sensor located over here on the side of the pit here. We've got gauges measuring load and strain and instruments looking at crack movement. So quite a range of different data types are being harvested from this this one site. I think to consider at this point is the options for linking those many sensor types. There are a couple of different wireless platform options that provide different benefits. A lot of the industry uses a LoRa platform very widely. Proprietary LoRa networks are widely available. They have some limitations, and in construction environments, we tend to prefer at Senceive, we tend to recommend a mesh-based platform, our flat mesh being our preferred option, because in many of these environments, we want to install a lot of sensors, often of different types, into a very dense network, and we want data in relatively high intensity, rapid sampling formats. So the flat mesh platform allows us to deliver all of that. It's also a self-healing system where individual elements can be damaged without damage to the overall system. So flat mesh is the basis of most of what we're talking about in this session today. Although it doesn't have to be, we can use LoRa as well. So looking a little bit more detail at some of these bits of kit in use here, zooming into that construction site environment, you can see here the geotechnical instruments. In this borehole, we could be putting various things. Could be a piezo, could be an IPI, could be an extensometer. If it's an analog system, it can be linked up to our millivolt integrator node, which can be integrated into the wireless system. If it's a digital output, then we can use the digital interface node to collate the data and to relay it through the network. The tilt node, well, this is the backbone, I think, of most remote condition monitoring systems. It measures movement to a high degree of precision. It can be fixed at any angle to pretty much anything. The sample in my hand, this is a nano macro. This is the biggest of a family of 3 nanos, and I think it's apparent that it's a lot smaller than those in the graphics that we can see here with a bit of artistic license. So in use here, we're looking at the stability of a crane base. We're looking at the integrity of a historic facade of a building here. Very versatile piece of kit used above and below ground for a wide range of different applications. Tilt nodes can be installed onto a linear fashion, onto a beam, a tilt beam, and in this way applied onto this sort of stainless steel this stainless steel beam, which gives us choices of different lengths. We've got joints that allow for thermal expansion, contraction, and we can use it, for example, where we're interested in looking at brickwork or masonry, where movement of individual blocks may not be representative of the structure as a whole. Or we could move it, or we would often mount it, for example, on a bridge, and we would look to mount it one end of it to a rigid point, such as the bridge pier, and then across the zone of movement, so that we can identify and determine displacement. And in the tunnel, you can see at the bottom of this graphic, the tilt beam is monitoring the relative movement of a number of segments. If we've applied individual nodes to each segment, we'd look at the movement of that segment. We use a beam, we can look at displacement in a linear sense, or arrange them radially around the arch. If we're interested in temperature, for example, of steel structures or curing of concrete, the temperature node can be integrated. Looking at temporary works props in a structure. These props are often used in braced excavations. They can it's important to understand what's going on inside the props in terms of strain and in terms of load. And this sort of application, you can see where a vibrating wire strain gauge has been fixed to the prop, and then up to 4 strain gauge sensors have been spot welded or glued to the steel prop. These are found to move a surprising amount with variations of temperature and load. And an interpretation of the strain gauge data can help us to determine the axial loading and the bending moments in the props. Reduces the risk of failure, but also it allows us to optimize the number of props that are used and to contribute, I think, quite significantly to lean construction. It's a lot easier to move big plant around the base of a pit if you've only got 8 props across it as opposed to 12, for example. You can see here the millivolt load sensor, where you've got a load pen integrated into the joint here, measuring load per ton in tons per pin. The crack sensor, we can see here in a simple arrangement, it's spanning across a crack, looking at relative movement. We can use a number of them. We can use 2 of them to look at slew and shear. So quite a useful piece of kit. Also gets used for looking at pile separation or structural movement or movement across a joint. So let's have a look at a few examples of these pieces of kit in action now. I've got a few snapshots of projects really. This is really just to give a taster, an overview of some of the applications. I'm going to start looking at some residential type properties and then move up to more civil engineering applications. So this is a residential development in the southeast of England, a town called Harpenden, and we're involved with the early stages of this project in terms of the demolition of existing buildings and the development of the foundations. So a relatively modest everyday kind of project, but still quite a complex site, because the team here were building a 5-story apartment building incorporating a basement car park. It's not particularly straightforward. It's an uneven site, and it's bounded by a couple of houses on both sides with residents in there concerned about the stability of their properties as these excavation works were taking place. There's also an historic grade 2 listed retaining wall adjacent to the site, and the authorities had demanded that that wasn't to be disturbed. So a fairly simple installation. We've put some nodes on tilt beams onto each of the properties here. This work was undertaken by RSK, as you could see from the logo at the start here. 14 triaxial tilt sensors attached to tilt beams on the two building walls. An additional 8 sensors on a tilt beam on the retaining wall. Things moved around a little bit as construction progressed, which is pretty typical of a project like this. But the sensors are installed in just a short time, just a few hours. largely they are wire and mains power free, so there's less chance of them getting snagged and having an issue. The data is relayed at 20-minute intervals to the people who are set up on the web monitor system. They would get alerts by text and email in the event of any movement beyond thresholds. And overall, it's the sort of thing which just supports the safe excavation. It protects the developer against potential liability. The residents of the adjacent properties were pretty pleased with it, really. The kit that was mounted on the house was pretty small and subtle and out of the way, and was removed as soon as everybody was happy that the work was done. So fairly simple operation, but a good way, I think, of providing assurance and probably speeding up the construction process because everybody is kept informed as it was going through. A couple more construction projects here. These are sites, both of these I think are sites where there have been concerns raised during construction about quality issues, and monitoring has been installed as a way of building an understanding, building an assurance that the structures that are being built are actually adequate. So you can see here some concrete columns where there have been issues with the concrete pour. There's a big notch out of this concrete column here, and a tilt node has been, an optical displacement sensor has been fixed to the column here, looking across at a solid object within the line of sight to look at the relative displacement of these objects. And these were fitted to a number of beams and columns around the site, along with tilt nodes and a gateway to provide the cellular coverage. A similar project here during construction. This is a site in Spain, as you can see, and again, the use on reinforced concrete structural members on columns and on beams. It's quite easy to put these highly robust sensors into place. You can see this has just been fixed here, and it's even been rendered around, and it provides that ability to understand what's going on when questions have been raised about the integrity of a project. Moving away from residential development, a little bit more towards civil engineering. In tunnel construction, obviously a major area of monitoring. Most big metro and most big tunneling projects in general around the world now will incorporate a level of wireless condition monitoring. They'll be used both to look at the structure itself and to look at third-party assets around the tunnel. And one aspect that is obviously a big concern is surface deformation. It's the presence or development of voiding that can cause sinkholes and damage. This is in Cologne back in 2009. I think every country around the world has experienced some degree of similar issues. In the UK, we had the collapse at Heathrow with the expansion of the London Underground tunnels into the airport. Virtually every country has encountered this at some point, and I think the increase in monitoring that we've seen over the last decade is partly to around the awareness and the concern that's been caused. And what happens in most situations here nowadays around the world, big projects, is that inclinometers, IPIs, will be used. They'll be used to look at ground movement immediately above the crown of the tunnel line, and they'll be used in proximity to it, to either side, extending below the line of the tunnel. And an array of these set out in advance will provide data indicating any sort of movement that's going on in the ground to a degree that's likely to cause a surface failure. Common practice historically was to use instruments with an analog output that would require some degree of logging and manual logging. The advent of digital loggers, such as the digital interface node Senceive launched last year, allows us to harvest that data from digital devices and relay it without needing to visit the site, and to relay it at a much higher data frequency. So clearly a much safer method on the left of harvesting your data than having to get out to site. Inside the tunnel, below the ground, wireless has also got a big role, I think. A lot of tunnel projects are using the technology in the tunnel itself. The small size, the flexibility of the sensors mean that it's well suited for use around the congested spaces around a tunnel boring machine. And an example of that is where certain tunnel boring machine construction operators, particularly those who use VMT for their convergence measurement system, will use a system which is based on Senceive tilt nodes. So if the construction is a precast segmental lining, there is a system here which has now been established and is used as an integral part of the VMT construction process around the world. It's integrated in with the TBM navigation systems, mature established approach now, in which sorry, let's go back there, in which 6 nodes, or a node, is attached to each of the segments, depending on how many there are around the arch, very close to the tunnel face. Within minutes or hours of the installation of the first ring, these can be installed, and this provides a high frequency of data in virtually real time, and it allows the engineers to see the effects of the initial settlement and of the injection and curing of the grout which is put into the annulus behind the segments in order to stabilize things. So minute by minute, hour by hour, as that process progresses, it's possible to see the changes and the increase in stability. And as soon as it reaches a level that everybody is comfortable with, the system will be taken down and generally just step forward onto the next phase behind the tunneling phase. Some of them will be left in place in some situations for long-term structural health monitoring. So a couple of rail related construction projects now. This is, as you can see, in Chicago. There's a major expansion of infrastructure around O'Hare Airport, and this involves highway and railway works which require significant excavations adjacent to a Class 1 railroad as part of this expansion. Among the many challenges here, there is the need to keep Union Pacific trains running just behind this fence at the top of the photo here. And it's a long-term project. There's been Senceive equipment installed on this site since 2022, and it probably will be there for some significant time to come. Right now, I think there are 20 nano tilt sensors installed on these beams, these steel shoring beams inside the excavation. And there are something like 400 nano tilt sensors installed on the sleepers, the track ties, looking at movement of the track itself. So the people working in these excavations are reassured that they've got an understanding of the stability of the temporary supports, and the people operating the railway have the assurance that the track geometry is not being unduly affected by the excavations. Another rail example. This is in the United Kingdom. It's a site on the East Coast Main Line, one of the 2 main north-south connectors in the UK. It's at Warrington, maybe 50 miles or so north of London. It involved another really complex infrastructure project, the construction of a large-scale under-track crossing. So a new twin-bore tunnel was being built for a new 660-meter dive under to take a freight line underneath the high-speed passenger line of one of the UK's busiest rail networks, rail tracks. it ticks the box, I think, of every sort of risk that we identified in slide 3 in the introduction. And it really enough to keep people awake at night for a couple of years as this project was designed and constructed. A number of things were undertaken here in terms of wireless monitoring. There were sensors installed, as you can see in the green circles, on the track. And there were sensors installed on the gantries. You can see here on the left, we've got an optical displacement sensor just above a cellular gateway here on one of the gantries, which will be looking across at a gantry on the opposite side of the track. In the middle, the photograph shows the solar panel, which is powering the cellular gateway. And on the right, we've got a close-up of the tilt nodes installed on the track. So this program went on for over a year. The kit was moved around the site flexibly as needs required, as the risk profile changed across this project. I think it resulted in a massive reduction in the exposure of people working on the track and the risks that entails. And it's definitely supported keeping the East Coast main line running throughout this extended construction period with minimal disruption. So that I think is the last of the little examples I wanted to just profile. And to close off this brief overview, I hope that this has demonstrated that the use of this technology can help in a number of ways, that it can help to reduce the risks or that it can address the multiple complex risks, this sort of tangled web of risks within a construction environment. I think I'd hope that we've demonstrated some of the advantages of IoT in terms of being small, easy, flexible, long life, low cost per year, flexible ability to take it down from one place to use it somewhere else, and the ability to provide high frequency sampling. For example, if you're looking at the stability of a retaining wall, where you can get data for sub-minute intervals. So hopefully that's done that. Hopefully we've highlighted that there's a growing range of sensors and interfaces there that can allow you to combine many different parameters and condition aspects of the construction site into one wireless system. I'm not going to argue that this is a replacement for conventional survey. I think this is very much to be seen as being something where 1 + 1 = 3. The different sort of families or philosophies of data collection are not competitive. I think they are complementary in terms of the precision, the absolute precision, the measurement of vertical movement. There's still a considerable way to go with wireless compared to conventional geodetic based survey. And I hope that I've demonstrated that through doing this, you can measure, if you measure the sort of risks, quantify the risks, and you can help to manage them. Risk removal may not be possible, but I think risk management is possible. So that pretty much brings me to a close. And I just wonder if there's any questions from that. Over to you, Amna.
Yeah, sure. Let me just open the question box. Yeah, we do have a few questions. So the first one, what are the options for the instruments at the end of the construction phase?
Yep, that's a good one. Obviously, construction projects can often go on just for a few weeks or a few months or even just a short number of years. And the lifetime of a wireless condition monitoring kit, the sensors can be many years, the gateways can be many years. So there are options there. One option, I think, is to hire the kit so that you can just hand it back to a provider at the end of your construction period. And very often, I think there are people doing very short-term projects where that takes place, and people will just use it for as little as 2 weeks. Another option, I think, is to use it somewhere else. Is to take it to your next construction project. Another one is just to keep it on a shelf and wait for an emergency to happen, because another application of this kit is to deal with unexpected events. So I think there's a number of options there, really, and hopefully it provides a sensible future use for the kit.
Okay, I've got another one. Have you looked into corrosion monitoring? This seems to be a hot topic lately.
Yeah, corrosion, that's an interesting one. I suppose I think corrosion is always an interesting one to detect and monitor, because very often I think the technologies that are there to assess it don't monitor corrosion itself. They monitor water content, they monitor changes in conductivity, they monitor changes in potential difference across locations. I think probably things based on potential measurement could be integrated into this sort of technology better than others. As it stands, it's not something we've actually integrated, to my knowledge, but I think that, if you pardon the pun, it potentially could be.
Okay, let's go through another one. So, is it possible to combine geotechnical logging with structural monitoring in the same system?
Yeah, okay. Yeah, I think certainly if you're using the flat mesh system, it's possible to have a whole bunch of different sensor types integrated into the same wireless platform, harvesting the data through the same gateway, and seeing it on the same web monitor instance. So yes, it's definitely possible to integrate things like IPIs and piezo's together with things that, for example, look at movement in the form of tilt sensors. A lot of our slope monitoring, which is a major application at the moment, in many instances that they will be looking at both movement using tilt sensors together with geotechnical data, subsurface data from IPIs, from piezo's. Okay, so last question. What if there is no cellular coverage inside a tunnel? Yep, yeah, phones don't tend to work terribly well in tunnels. In that situation, there are a few different choices. A lot of new tunnel constructions sites will have Wi-Fi. In our experience, I think most new construction projects of scale around the world will have a Wi-Fi system, and we can jump onto that. We can use repeater nodes alternatively, so that we can stick with our conventional wireless approach and transmit the data out from the site. And in that particular case, we would generally choose a LoRaWAN based system, as opposed to the mesh-based flat mesh system, so you get longer range. Alternatively, we can port the data into a data hub and download it later, if you're not interested in very short-term high-frequency reporting. So, yeah, there's generally a way of getting data from underground, whether that's in a tunnel, whether that's in a mine or some other subsurface environment. Okay, we've got another question. Well, we're having a few questions coming actually now, so let me just go through those. Assuming the Wi-Fi connection rely on the local service providers, is there a plan B in case the local system failed? And how long does it take the system to reboot in case of failure? The first backup is that the gateway will store data typically up to 30 days. So if it's not able to export its data directly from the gateway because of a failure of the cellular network, then you have got the option of manually going to site and downloading, or it being transmitted when the system is back up. And in most situations, that is the effective route. How long does the system take to come back up? It's going to depend on the network it's on. It's going to depend on how many sensors are on it. It's going to depend on how quickly people were aware of it after the failure. I'm probably not the best person to answer what that is typically, because it's probably better that somebody in our customer support team who's regularly dealing with that would answer it. So I don't want to say a factual answer to that one, but it wouldn't be very long. You know, if you're aware of it, if it's been flagged up with an alert, which of course it would be, then it should just be you know, minutes or hours to get it rebooted and back up and running. It should be less than hours, really. Should just be within minutes, as long as people are aware.
Okay. So another one here. Are there any inbuilt redundancies in the mesh system against a sensor malfunction?
Yeah, I think it is one of the inherent advantages of a mesh-based platform, in that if you have, say, 100 sensors all talking to each other with a number of connections, a number of routes back to the gateway, if one of those paths is permanently or temporarily cut because of the failure of one of those sensors, one of those node points, then either the data will just find the next best way back to the gateway. It will, as long as the sensors have been located in a way that there's not too big a hop between the locations, and we would generally provide advice on that in any particular site, making sure that you've got a bit of redundancy built into the spacing of the sensors. Yeah, if one goes down, an alternative path will be found. You don't have to touch it. You don't have to do anything. Within minutes, the system will self-heal and find the best way back to the gateway.
I was on mute there. I saw that pop up. I was like, yeah, I'm on mute. So I was just saying, the last question is how the sensors can be placed in linear utilities, so water, sewage, gas lines.
Yeah, being placed in them. I effectively, if there is access, if you can get in there, if you can install them. I mean, I guess it's really an environment which is basically a small tunnel. That's what we're talking about, and it would be used in the same way as in a smaller tunnel. If we're talking subterranean, if we're talking buried pipes and services. Yeah, I think you'd have to look at it case by case, because it would be, you know, there is the issue of getting in there to mount them. And generally speaking, I'm not aware that we've ever done that with any robotic installation. It's always been getting a person in there. Then there's the matter of getting the data out. So yeah, the same issues would apply in terms of a tunnel monitoring program, where you'd have to look at those sort of plan B, C, and D to get data out of the tunnel if you didn't have cellular. So yeah, it could be done. It just depends on getting access, and it depends on getting a decent sort of signal out of that environment.
Perfect. Thank you, Simon. Yeah, I think I got through all of the questions. But if anyone does have any more questions, you can email them to us at info@senceive.com, and we'll have someone get back to you. Yeah, so one more thing from me, just wanted to say, please keep an eye out for our July webinar, which we will be announcing soon. So thank you very much, Simon. Thank you everyone for joining us for this webinar, and I hope you have a lovely rest of the day. Thank you so much. Bye.